I'm going to make this a very quick introduction, and I am so excited to welcome our two guests. We have Professor Eugenio Ursino, Assistant Professor of Physics at PFW here, and then my intern at Science Central, Nadia Watkins. She is in her senior year here at PFW. She is majoring in physics and has a concentration or a minor in astronomy. That's correct. And her internship at Science Central is through the Indiana Space Grant Consortium. So she's a NASA intern. And I'm very, very happy to see her present today. So I'm going to leave all the details of WHIM, or the Warm Hot Intergalactic Medium, up to you two. You'll go first and then Nadia second, right?
Yep, that is
perfect. Good. Thank you. I'm going to leave this right here.
I think I have this one. I hope it's working. So good evening, everyone. We already had some introduction of the general topic that we are going to discuss, but I would just go with a brief introduction of what is going to be. So Nadia asked me if I wanted to be part of this presentation this evening. And I said, yeah, why not? So she's been working with me for a while, helping me in my research, and so I thought, well, it sort of makes sense that she wanted to talk about what she's doing. And I said, well, I will go with a general introduction of X-ray astronomy, or the part of X-ray astronomy that we are doing at Purdue Fort Wayne. And then she will go deeper into what she's doing and how she is taking part into the larger community of X-ray astrophysicists. So, even the main topic of my research is the WHIM that has already been mentioned that I will go through. There are many, many aspects of X-rays that I will go through, but I will be kind of quick, and I will also show you why I need to talk about everything else before we go to the WHIM. Okay, so first thing is defining what is the X-ray sky. So we can see light, but there is a much more light that we cannot see. And that's pretty much the full electromagnetic spectrum, and goes in all those forms of invisible light that we have names like radio waves or infrared, ultraviolet. We have also X-rays, and then go into higher energy, that is gamma rays. But also for X-rays, in general, it's like we can see, say, 7 colors, that is the rainbow. Say that for X-rays, you have 1,000 different colors. That's the large kind of an idea of how large is the gamma of different colors, the range of different colors that you have. So essentially, we in the community, we divide, at least in the lowest energy part, so that is the part that is closer to the visible, still very far away from being visible. And that's the part that is interesting for me. One thing that is very interesting about light in general, that is light is also connected to the size of the objects that you are looking at, that is responsible of the origin of that signal. And X-rays, well, we call them X-rays, but we can measure it in different ways. They are wave, so we can use wavelengths, but since they are waves, so because the energy of a wave is proportional to the frequency, we can also use electron volts. In X-rays, we usually go with electron volts just because it's a number that is nice to say. I use about 1,000 electron volts. If I had to use, say, meters, that doesn't sound that nice. If I use frequency, I have to use 10 to the 17 hertz. 1,000 is way better. So since we want to, we use different units just because it's easier to handle 1,000 rather than 1 billion. So that's why you will often hear from me using electron volts. But just the idea is because it's a relatively large number. But the counterpart is about 10 to the negative 9, 10 to the negative 10 meters. That is the size of an atom. Not in this slide, it's that usually the wavelength corresponds also to a temperature. If we describe objects like black bodies have a peak temperature that corresponds to some energy. We can convert the energy, the temperature energy into light energy, and it's about 1,000,000 degrees or a few million degrees Kelvin. If you want to convert to other things, well, just you multiply by 2 and you get it in Fahrenheit. So what I'm going to describe is something that is usually in the range of a few million degrees if I use temperatures, or hundreds to 1,000 electron volts if I'm using energy. This is the kind of language that I will be using. The other thing is, why is it so hard to study X-rays? Atmosphere. The atmosphere, well, you know, it's good because it lets us see the sun. We can get the light from the sun, but it blocks most of the light of the sun, actually. It blocks the UV, it blocks X-rays that would be harmful to have for our life. It also blocks other ways, but the most important thing for me is it blocks X-rays. So yes, I'm glad it blocks X-rays because I'm alive. But if I want to study the night sky, or, well, the sky in the X-rays, I have to send something above the atmosphere. I cannot use a ground-based telescope. I cannot use a telescope that is on the top of a mountain. It's not yet high enough. I cannot use a telescope that is on an airplane. They did it for infrared, but it's still too low. I cannot use balloons. They're still too low. We need to go 100 kilometers high. So there are only two options. Either we use a rocket that flies up there for a few minutes and you can collect light. That's not what I do. Or we use satellites that stays there for very long times. The kind of pictures that are useful for me, usually you have the X-ray camera that is pointing to an object for 1 or 2 days, just constantly taking images from that one. So you have, when I'm saying, okay, what is the exposure time? We go from the kiloseconds to the megaseconds, just to give ideas of how different it is from, say, what we can do with our telescopes from the neighborhood. So actually, I'm starting with something that is completely different, and that is the cosmic microwave background. But this is introducing the problem why I'm interested in X-rays. Well, we start from looking at the cosmic microwave background that is telling us what the universe was like at the beginning, about when it was 400,000 years old. This picture is kind of misleading because you see a lot of contrast in here. Actually, when they show us this picture of the cosmic microwave around the average. Say you're looking at something that is this high, but instead of looking at that, you just look at the peaks and troughs that are around here. That's what I show you. So they take away the average and they just show you, okay, this is the gaps that you have from the top and the bottom. The point is that the average value, if you convert it to temperature, is the temperature of the are about 18 microkelvin. That is 18 millionth of a Kelvin. That means that the tiny fluctuation that you have around this one is actually, I cannot make that thin with my fingers. Okay, the kind of fluctuation. That is what we see from there. So once we know what we are looking at that one, that means we're looking at regions in the sky that are slightly hotter or slightly warm, or colder, or slightly higher density or slightly lower density, but the differences are extremely tiny. But doing models, that's not what I do. With models, they have been able to understand a lot of the universe from just this picture. And among other things, this picture can tell us what the universe is made of. And so we have this pie chart that is telling us almost 70% is this mysterious dark energy. We don't know what it is. Okay, it's not my problem right now. 27%, give or take, is dark matter. Again, it's somewhat related to what I do, but not my thing, because it doesn't emit any light at all. That's why it is dark matter. The rest is what we call ordinary matter or baryons, baryonic matter. Just this morning, or this afternoon, I had in a class discussion with a student. I was saying, okay, you are saying baryons, but what do we mean with baryons? Baryons are regular matter, what we are made of. So what we are made of is only about 5% of the whole universe. From that plot, that's what we know. We know that the whole universe, only 5% of it is what we are made of. Everything else is something else. That's not my problem, that's some other astronomer's problem. My problem is that when we go with different telescopes, like the Hubble telescope, and we take pictures, we have these nice pictures with all the objects here and there. And first thing that we see is, oh, now there is a huge contrast, because the regions that are bright, they are very high density. And the regions where we don't see anything, it's very low density. The previous picture, the difference between high density and low density was the tiny difference like this. Now it's huge difference. It's like low density is down here, high density is the top of the building, just to get you on how much it has changed. And same thing in temperature. So the universe has changed a lot. Initially, it was almost perfectly uniform. Now you have regions in the sky that are very high density and very low density. The other thing is, if we use the light of the objects as a proxy of how much matter is in there, we see that we find only about half of the expected regular matter that we had from here. Here was saying we have 5% of the total. From here, we find only 2.5% of the total. The other 2.5, we cannot see it. Why is that we cannot see the other part of matter? It has to be there, because the laws of physics are telling us matter does not disappear. It is there somewhere, and we don't see it. Why? So that's where, just to tackle these two problems, how is that the universe became so different? Well, so diverse, no longer uniform, but high and low density. And where is this missing matter? So we have a problem of, we call it the missing baryons problems, because this matter is there, but we don't see it. It's missing. So essentially, well, I'm just skipping on this one because it's repeating what I did. They started creating computer simulations. They are using a model of the universe, usually it's a box, the size of a few 100 million light years. Well, I would say several 100 million light years. They put a bunch of particles that are actually the size of a fraction of a galaxy, and then they let the physics drive it. And they start with conditions that are sort of similar to the initial universe, so almost perfectly uniform with just a few tiny changes, and then they let physics go. Physics is mostly gravitational force. And we know that where is higher density, it's pulling matter towards higher density, and so it's going away from the lower density. And we can already see there is a mechanism so that regions that are low, initially slightly lower density, now become a lot less density because matter is going away from there. And regions that were slightly higher density, they are collecting matter from the neighborhood and they become very high density. On top of that one, we see that also matter that goes in these regions that are attracting matter, they become hotter and hotter. So this plot here is just a plot from one of the many simulations that is showing us gas that is below 10,000 Kelvin and above, 100,000 Kelvin and above 100,000 Kelvin. For me, this is cold gas. And what we have in here is just separation through time. So the simulation starts from the early universe. Then we have redshift 3, that means somewhat relatively recent universe, and getting up to present day. And we see originally all the matter was diffuse and relatively cold. And there was very little matter that was a little bit warmer and in this kind of structure.
Oh, the
That's
rocket.
live?
Yeah.
This guy, I forget who was supposed to talk tonight. Why are you getting those cookies when you got all these?
She wants, they're new.
Whoever is speaking on the Zoom, if you could mute your microphone, that would be really appreciated. We can hear you. We can hear your conversation, so please mute your
I
microphone.
should know that.
Mute them. Oh, suppose we could.
You can go to participants.
Mm-hmm.
You can mute everything.
Yeah. Mute. No, mute. Okay.
Oh,
I haven't been muting people in a long, long time.
How do you do it, Jim?
Huh?
How do you do it? You just have to click on their microphone?
I don't hear anything.
Because those, okay.
You got it?
No,
No.
Okay, I'm sorry.
or is it all?
Here, I'm gonna
everyone?
claim host here.
Oh,
Can't forget that. I know once.
is it just muting their?
I'm just looking for green. Everybody is, oh, gotta mute this person. Hey,
Yeah, it doesn't let me.
oh, that's because she's the host
Okay.
for some reason.
Hmm.
And I can't reclaim the host
Okay,
without
well, let's
knowing
continue then.
passwords. So we just,
You can edit this out.
yeah. Okay.
Sorry about that.
Yeah, no, it happens. I've been through that also with my students in the past, so I know. But so we're saying here is the warmer gas that already is showing some sort of structure. And what happens with time, matter goes from low density to high density, but the high density is also warmer. So the gas here that was cold and diffused starts going into the hotter and more higher density region. So you see that gas is, the pattern here is getting more and more matter in here, and here it's getting empty. So this is how the universe has been evolving from something that was diffused to something that is showing structure. So we expect that the universe has a structure like this one, and actually have been, even before they did simulations, they were already mapping the distribution of galaxies. And I did see that indeed the galaxies are aligned along these structures. It's like sort of a sponge, if you want, or just a large number of tendrils and filaments that are crossing each other. And where they cross, you have clusters of galaxies. So that is pretty much where I started doing my research at the time, when we had something like this. And I was mostly interested in this part, that warmer part that is filamentary. Because one thing is making a little bit more in terms of numbers. How much of the original gas, that was the colder diffuse gas, is still there? But half of that is still the cold and diffuse gas. But almost half of that goes into that filamentary structure. And then there is maybe 10% that is in clusters of galaxies. Now, clusters of galaxies are nice, extremely high density, very hot. They emit a huge amount of X-rays. We can see them very well. The thing is, instead, this filamentary structure is in a temperature range that is about 1 million degrees. Now, if you remember, I was telling you about 1 million degrees is the soft X-rays. So the idea is, if these things exist, they should emit these soft X-rays. So the plan is, let's look at the sky in the soft X-rays and look for these guys. Well, according to our investigation of how much regular matter is in the universe, we have been able to account for matter in many sources of light. But still, well, so the original 50% of it is missing. We have been improving a lot. Now about 30% is missing. The 30% is still, if there is that thing that is emitting these soft X-rays, we expect to fill this gray region. Okay, if they exist and if we can see them, they should fit in there. So the problem is still, okay, we still have these guys that we don't see. So why is that we don't see them? We have been trying, but the point is that in the same soft X-ray band, there is a lot of stuff that is emitting, together with the WHIM, starting from very local. The most local thing that we have is this thing that is called the solar wind charge exchange. It is interaction between the solar wind and the environment of the solar system that is going through essentially collision between these particles. They get excited, and when they get excited, they emit X-rays. Kind of the same X-rays that we expect to see from 1,000,000 degrees gas, that is the distant WHIM. Then we have what we call the local hot bubble. I will go next with a better slide, but that gas is kind of locally is in the neighborhood of the solar system, about 100 light years away from us. And it's about 1,000,000 degrees, exactly the same temperature of the distant thing that we are looking for. Then there is this region that is the gas in the galaxy that is absorbing light from far away. So light from far away needs to go across the galaxy. It becomes dimmer, harder to see. Right outside of the galaxy, there is this region that is the galactic halo, circumgalactic halo. It's part of the, we don't know exactly if it is the outer part or still within the galaxy. Again, a few million degrees. Exactly the same temperature of the distant thing that we are looking at. But these things are very close. Being close, they are brighter. Just like anything that is closer to us looks brighter. So the point is, according to our models, in the best case scenario, the combined thing of all these filaments is about 10% of the total X-ray emission that we can see. But that's a combined emission of all the filaments. That means that one individual filament is extremely dim, extremely faint. And it's almost impossible to see it because you have a lot of light in front of it. Something else that is emitting the huge amount of light in front of it. So that is where the big problem for people that are working in the same field as I'm working, that is the biggest problem that we are facing. We have other things. And so for most of the astronomers, what I'm studying is just a background light that they want to remove because they want to observe the bright sources. For me, instead, I want to get rid of the bright sources and just have this very faint light and being able to observe it. So if I want to observe it, we only have one option that is left, and that is try to understand as best as we can how everything else that is in front, how it behaves. If we know how these things behave, in a sense, we can remove it from the total signal, and what is left, we can use to understand this part. So now I'm going with a little bit of a discussion of what these other components are, and then I will just get started with the WHIM, and at this point, I will leave it to Nadia also, before it gets too late. So quick thing for the local bubble, initially was called the local cavity. In the 50s, they found that there was this region around the sun that was kind of empty of cold gas. You have cold gas that are these red regions, kind of far away. And then there was this cavity. At the end of the 90s, they figured out that it's not empty, it's just full of 1,000,000 degrees gas. So the 1,000,000 degrees gas has been pushing apart the colder gas. Why we have gas in there? Some big supernova explosions in the past. Millions of years ago, there has been some supernova explosions. So what we have here is the hot gas is the leftover of those explosions. Being 1,000,000 degrees, soft X-rays. And again, we have been looking at sort of a map of what this local hot bubble looks like. Actually, it's interesting because it's more like an hourglass shape rather than anything else. And actually, this profile has been part of an investigation that my thesis advisors and others did. I just helped a little bit, but it was not my work. So using X-rays, they mapped the shape of this, or sort of a cross-section of the local bubble. It looks like that we are very close to the center. That's just by pure chance. And this instead is pictures from other wavelengths. I think that is from visible light. But it's interesting because you see shapes. Here we have colder gas, and you see that our profile of the hot gas is not in there. Actually, one thing that I always loved is just this part here. There is this gap, and you see the hot gas that goes into there. Then the other part that is the Milky Way contribution. Now, if we look at a cross section of the Milky Way, well, we are just on one arm of the spirals, kind of far away from the midway, far away from the center. We have the galactic center in here where there is the bulge and some gas, but there is also this halo and part of the disk. Now, I'm not showing much more because quite honestly, we don't know yet what this galactic halo is. Some call it the circumgalactic halo, meaning that it's kind of relatively far away from the center. But according to other models, instead, is mostly close to the plane of the galaxy. So I'm just leaving as it is in this picture without going into further details because I leave it open to all options. But just to remind us that there's a lot of gas from the Milky Way galaxy itself. Gas that is about 3 million degrees. So it becomes an extremely strong source competing with the WHIM. So at this point, where do I stand with these things here? So I'm interested in the WHIM, and I'm interested in looking at the X-ray emission from the WHIM. So what I did in the past was starting from simulations, try to simulate what would be an observation with an X-ray telescope. And the idea is that if you look along a line of sight with an aperture that's say about 1 degree by 1 degree, you start seeing an overlap of many filaments. It's extremely hard to have just one individual filament that is brighter, but you start stacking. So what I have in here is the picture from everything that is close, relatively close to us, to as far as we can see. And when you start stacking these things up, you see some things that are kind of patchy. Actually, here is a little bit misleading because this part here is representing more the contribution of galaxy clusters. This is more the pure filamentary part, but it's still patchy. This is the sum of the two images, just one on top of the other, because the actual sky is this plus this. But the plan that I had at the time is, okay, if I want to study this, I can get this image, get rid of the brightest part that is this one, and what I'm left, it's somewhat a true filamentary sky. Like I said, you don't see the filaments, you just see the superposition of all these filaments. So unless you're extremely lucky, because there are methods to say, okay, I know there are two clusters here, I have a very focused picture in this area in between, and if I'm lucky, I can see the filament. I did that when I was a grad student, other people did, nobody ever found the filament. We haven't been able to see a filament. But the idea is instead, okay, if we have something like this that is patchy, in a sense, it's very similar to the cosmic microwave background picture that I showed you at the beginning. And they use some tools to extract information from that picture. So what I'm trying to do now is mostly focusing on trying to use similar tools to get information from this patchy shape. The patchy shape is still carrying information about the WHIM itself. So that is one way of looking at it. The other option is instead, well, say that I'm trying to go through something and say that I'm lucky enough that I have in one of my pixels a filament. So what I can do, since X-ray telescopes in this sense are getting better and better in energy resolution, I can do spectroscopy. I know that you can do that, so you know what I'm talking about. With X-rays, we can do spectroscopy in both emission or absorption. Actually, absorption has been done. They use active galactic nuclei from the background, and if there is a filament in between, they can see the absorption features, and that is telling us, oh, there is a filament here that is the red lines, and there is another one that is the blue lines. But the idea is that First of all, the filaments are emitting light. So if I don't have anything in the background and I have only a filament and I do the spectroscopy, I should be able to see the peaks from the filament, from all the elements and the ions in the filament. So here, what I have in this picture here is two things. The green line is actually the combination of the local bubble and the galaxy, the Milky Way galaxy, what we call the galactic halo. That is the baseline where we need to go above in order to see something. So the average signal from the WHIM, it's too low. Here is at least 10 times lower. But if we are lucky and there is one element that is emitting a strong line, that line goes above the Milky Way and local bubble contribution, and we can see at precisely that energy. That tells us that, for example, oxygen, when you remove 6 electrons from oxygen, that's what we call oxygen 7, and emits a triplet, so 3 lines very close to each other. This is the one from the Milky Way galaxy, and this is one example of a filament that, since it is redshifted or it is far away, at this point it's so far away that we have the redshift due to the cosmological expansion. So essentially, we can see the same oxygen line, instead of being overlapping to that one, is shifted to a different position. That's just because objects that are far away, it's like they are moving away from us. And so because of the Doppler effect, their light is shifted. So the peaks that we are looking at are shifted. By looking at the shifts, we can measure how far they are. We are using Hubble's law. So I can know how far away this object is, and I can also get some estimate because the ratio between these lines tells me what is the temperature of the gas and what it is made of, because if I find oxygen 7 here, and this is the oxygen where we remove 7 electrons, and there is only 1 left, we call it oxygen 8. But then we also have other lines from iron, a huge number of ions. Now, this is my model that I made several years ago, and we were using some physics. Now, at this point, we realized that there is something new, and that's part of what Nadia is doing now. So at this point, I'm stopping here because what she's doing is actually investigating better what happens in here, because there is some new physics that we identified recently that is acting in the X-rays. So I will take a break here and have Nadia join me. And I guess we need to switch screen. Yep. It's this one, right? So yeah, I'm going to stop share this, but I stop sharing and go share the new one. And it's sharing this. There. And here you are.
Hello, everybody. My name is Nadia, and we're going to be looking at the effects of resonance scattering on WHIM. I've been working on this with Dr. Ursino, who's been talking this whole time. And I'm going to skip a little bit because some of the things that I have on my presentation, he already explained. So, okay. So I'm going to start with what resonant scattering is. So basically, it is a background source source that emits radiation and reaches a filament. This radiation would excite the ions in the filament, and once it de-excites, they would emit X-rays that we could then see. So all ions go through resonant scattering, but because they're all affected equally, but they all would emit to us in different ways. So we cannot see every ion that is, we can't see every ion the exact same way. So the picture that we're looking at, it shows an example of what resonant scattering would look like. So obviously when light is absorbed from a star, we can then see those lines. We would consider this our field of view, and we could see those lines very easily. Emission, when those lines are emitted back to us, we can see those. But what resonant scattering does, it takes a light from a star or a source that we wouldn't normally see, and it kind of redirects it towards us, and it makes it easier for it to see. So with that, the goals of my project have been to find how much resonant scattering contributes to WHIM emission, because it's not easily seen. Again, it gets clouded or overlooked, overshadowed by other things in our cosmic background. I want to model all emission contribution from WHIM. And then I look at the scattering of specific ions, carbon, oxygen, such as carbon, oxygen, iron, and neon. I'm specifically looking at oxygen 7 right now. And I'm looking at these in different redshifts. And from this, we hope to identify the ratio of resonant scattering to total thermal emission. So my methods of how I do this. So I'm using a simulator called Cloudy, and I'm using it specifically to simulate emission from WHIM filaments, but it can be used for other things. So it's able to simulate temperature, density, a fixed geometry, and at specific parameters. And from this, basically what I would do is I would create my in file, which I put all the parameters that I wanted to have, the specific temperature ranges, the density ranges, and everything else that I would want it to have. And it would read that, simulate all of the emission spectra from those parameters, and I would get 3 different files. I get an output file, which basically would give me all of my data. It basically goes through every time it would read and simulate the code, it would give me all of that data. So it's a very big file. I get the grid file, which gives the temperature and density ranges that I gave it. And then I get the con file, which pretty much just shows my entire spectral lines for every ion in the WHIM filaments. So testing. What I'm doing is I'm testing different combinations of temperature and density. So I'm using 30 different temperatures and 30 densities when I'm comparing these. And right now I'm focusing on oxygen 7. Oh, it's actually 31 temperatures and 31 densities. I'm sorry. And from that, I'm comparing the effects of resonant scattering on versus no resonant scattering to basically see if there's a big difference in, you know, how much of that specific ion that we're able to see. And at the time, I was only using redshift 0, but I've since expanded to using redshift. I'm using 0.3, 0.5, and I think 1. So this is a example of what my in file looks like. I'm specifically focusing on the metallicity. So we're using metallicity 0.3, but that's up higher. It's kind of just cut off. We will look at no induced processing, which basically turns the resonance scattering on and off. And then I am specifically changing the Z, which changes our redshift as well. So that would be the different parameters that I am changing. Everything else that you see stays the same for every single simulation that I run. And then I'm actually going to come back to this because this is an example of my code that I'm using to run that. So to read those simulations, the com files can, obviously I'm simulating every ion in those WHIM filaments. So the file can be very big. Mine is usually about 50 gigabytes, but I've seen Dr. Ursino's be closer to 80 or even larger, depending on how many parameters he uses. So I had to come up with a Python code, which Natalie, who was a previous student working on this project, she started it, and I have modified it to work for my specific temperatures and densities. Well, my specific parameters that I'm using. So this is an example of when I ran that code, what my reflected, my WHIM filament for oxygen 7 would look like. So it shows, this is for resonance scattering on, and it shows what that filament would look at these specific temperatures and densities. So my temperature range is usually from 4 to 7 on a logarithmic scale, and the density is about -4 to -7. So going back to that code, this is just a little snippet of it, but basically what I am doing is I'm calling the con file. It pretty much reads the con file and looks for my specific ions that I want to, it looks at my specific ions that I want to look at. So for this one, oxygen 7, it reads that, looks at the specific temperatures and densities, and it's able to make that picture or my simulation from that. And then, so what we were just looking at was my resonance scattering on. And then this is an example of my non-resonance scattering and my ratio map that I got from that. My ratio map is not very correct. My continuum is kind of off, so I'm still messing with that and trying to fix that. That's something that I've been working on. And then my to-do list, what I am currently working on. So obviously debugging my code, because it has a lot of little issues such as my continuum being off and my ratio map not looking exactly how I need it to look. And then I wanted to start looking at other ions, and we've recently been obviously looking at different redshifts and different resonance scatterings. I'm sorry, that doesn't make sense. But yeah, different redshifts and different metallicities. But yeah, sorry. That's pretty much it. Were there any questions? Thank you. Yes.
What the program you use?
Oh, yes. I'm using Cloudy to simulate everything. Yes, sorry. Yes. There are many different ions that we could have chose. So we're looking at, I just began with oxygen 7 because when I took this over from Natalie, she was already working with oxygen 7. Yeah, which one? Oh, the slides I did not show. Yes.
Okay. Well, essentially, oxygen 7. Oh, please, thank you. The idea is that oxygen 7 is the brightest, the strongest line that is emitted by a gas about 1,000,000 degrees. So it's the easiest to see.
What is that?
Oxygen 7.
Yes.
And the second one is oxygen 8.
Yes.
So that's why we started with oxygen 7. And then the evolution of the program is looking at oxygen 8 and then other lines that are in here. But just a few lines can go through the resonance scattering.
Was that the analog of the Balmer series?
Well, it is related to that one, but essentially it is, in a sense, the Balmer series, just with different names. Yes. And the idea is that resonance scattering just goes on top of this. That's why we recently realized that there should be resonance scattering. If resonance scattering is there, these lines should be way higher.
Mentioned the collision process, the winds for acting. Is that different than this resonance scattering? It sounds like it's different.
It is way different.
Mm-hmm.
It is, so that is the solar wind charge exchange. That is a completely different project effect. So it is during the collision, one of the atoms get actually excited, and then well, also loses one electron and gets excited. And then what is left over de-excites and emits the X-ray photon. So it's not the same as the thermal process that is responsible for these lines. These lines are just the standard excitation and de-excitation of atoms of ions. So this is, usually you have a collision between an atom or say two ions. Because of the collision, one of the electrons goes to a higher orbital and goes back. For a solar wind charge exchange, there is actually exchange of charge. So one electron goes from one particle to the other particle, and as a result of that, it goes also to an excited state and then de-excites. So there is an actual transfer of charge. In here is only a collision, so that they are not transferring anything except for a little bit of energy.
In the resonant mode, said that it requires a source, apparently of a higher energy X-ray to excite the gas with the X-rays coming out of it. So what's the source of the higher energy?
Well, it doesn't necessarily be higher energy. It can be any source that is distant source, like quasars, AGN, that are emitting X-rays. So the X-ray photon of the right energy, that is exactly this energy. So the point is, if you are there, the AGN is emitting some photons this way. They jump here, they excite the photon, they excite the atom in here. This one is exciting and sending light randomly. Some of that light goes back to you.
How dense are these clouds that are being inflated? How dense are these filaments? How many atoms per?
Well, let's say in terms of, yeah, that's something that I didn't mention in my presentation, but the density of the filaments, it's about, we have a lot of discussion within the community, but no more than 1,000 times the density of the universe. So talking about atoms per meter cube, maybe 1,000. So that is some of the lowest density thing that we have in the universe.
Remind us what the density is in a planetary nebula.
Planetary nebula, I don't have the numbers on top of my mind,
Oh,
but that is probably definitely more than 1 million. It is maybe 1,000 or 1,000,000 times higher density. Much, much higher than here. Like I said, the planetary nebula is inside a galaxy, inside a cluster, and clusters are 100 times denser than this. Planetary nebula, we are talking about, in terms of astronomy, a high density region.
So what's the field of view of an X-ray telescope? It would seem, optical, you have to have really gigantic ears and things, get a lot of reach.
Yep.
And X-rays are so much smaller in wavelength.
Well,
so can you get really high resolution X-ray telescopes relatively?
Chandra, in terms of angular resolution, it's 2 or 3 arc seconds.
Better than radio.
Yes. Radio is the worst. Yeah, no, radio is definitely the worst with X-ray, because the problem with a resolution, it gets better actually at higher, shorter wavelengths. The shortest the wavelength, the better the resolution. But the problem is now having a detector that works. X-ray detectors have a problem, or mirrors have a problem. If you use your regular mirror with light, bounces back. If you use your regular mirror with X-rays, it gets absorbed. For an X-ray mirror, it's actually not a mirror, but it's like more like a funnel. You have these mirrors, light comes just grazing it, just changes slightly the angle. So you need to have a nest of mirrors that are slowly steering the photons towards the camera. So these mirrors have to be very long because they are more like pipes than actual mirrors. And that's part of the big problems that we have with X-rays. Beyond sending them in orbit, they must also have this very special design. So an X-ray telescope just easily go close to the $1 billion budget. Maybe half of that, depending on what kind of science, how precise you want to be. But that's kind of that number. So that's the kind of project, if you want to go through that one, usually goes to the Senate to approve the budget. Well, this is all simulations. But what I did in the past, I used more the XMM Newton telescope, the European counterpart, because for the imaging for WHIM, it was better. It has less noise. Chandra is better for angular resolution. But these filaments have the size of, say, 10 arc minutes. So if you have the angular resolution of 3 arc seconds or 10, it's not a big deal. But having the XMM Newton has way less noise. So the noise that, on top of this, you also need to include the instrument noise. That is kind of this level. So Chandra is higher level. So that's essentially why I used mostly XMM Newton. Also, XMM Newton has a larger collecting area. That means it takes less time to get the number of photons that you need. And here, when I'm saying that for this signal here, we are just counting a few photons per second. That's so completely different from the kind of images that you have that you don't even count the seconds when you do pictures in the visible. You just measure the energy, how much is the intensity there. In here, we count the seconds.
Are there any calibration sources for the prove your simulations are actually correct? What do they look like? Because you're really high energy levels, right? So,
well, no, they don't just to calibrate all these things. It's mostly from NIST, and then there's a very large number of institutes. So what I do, I use other tools that generates for, say you have a gas with this temperature and density, it creates the spectrum for me. What I do, I collect many particles, each with its own temperature and density, and add them, all of them. That's what I do. But the calibration comes from software that others did. And that all goes through NIST or similar institutions.
Yeah, earlier you talked about the baryonic pattern, 5%. And the question was, you say that was, that you could determine that from the cosmic background map?
Yes.
I don't understand how that's possible, but if it's a long explanation, I accept it.
Well, there is something in there that is missing. And I don't have anything to draw, but maybe you have some pictures of the power spectrum of the cosmic microwave background. It's some sort of they represent a thing with a wave that has a high peak, that is the peak at 1 degree. That is the thing that I used to prove that the universe is flat, the 1 degree. But there are also other peaks. If you remember, it is something with many peaks. The ratio between these peaks and the heights tell us how much dark matter we have and how much regular matter we have,
Okay.
and how much dark energy. So I cannot go more into the details because some of those, it's not even the science that I do.
Yeah,
But
sure.
from those peaks, you can estimate the
From the,
number.
like the power spectrum.
Exactly. The power spectrum, it's modeled on many parameters. So what they did, they generated a fake universe with different values. And the one that was resulting the power spectrum closest to the observed one, they said, okay, that is. So that's how they did it. They just generated random universes with different parameters.
Yeah.
And the one that had the closest power spectrum to the one that was observed, we say, okay, that is very likely the best approximation of our universe.
Amazing.
No. X-rays with polarization is something that is very recent. They launched IRXE, that is the X-ray polarimeter, just a few years ago. It's the first X-ray telescope that can measure polarization, but we don't expect to have it, at least in this environment. Biggest point is we haven't been able to see one filament. I would say if I could see a filament, I would also use that one and see any properties, because then magnetic fields and everything else, that would be huge.
Right.
But right now, first I need to see one filament. Once I have a filament, I can say, okay, now also let's study the polarization on that one. But they have now, it's very recent, they are studying many things, but not the filaments because we don't see the filaments.
Anyone else? Wow, thank you very much. That was very interesting. Thank you. And good luck. Great. Yeah, I'll stop sharing. Yeah,
Bottom.
there we go.
Okay.
All right.
And then contrast.
Fascinating. A lot of spectroscopic questions that I didn't get to just because I don't want to bog us down. I've done a little bit of it, so appreciate that. Okay. Sure. Yeah. I'll get with you. Thanks again. So the next phase of this evening's meeting would be show and tell. If we have some images that would like to share, either electronic or physical, that would be okay. Come on up, or anybody online that has any images they would like to share, pop up and let us know. Dale, you had something? All right. You get a microphone. Go ahead.
The things I brought are
Yeah.
the things I brought are physical instead of digital. So I will, hopefully we can get a good view in the camera there. But I do lots of work over the years with Lindenwood Nature Preserve, and this last year they actually featured the images I've taken with my telescopes and stuff in a cool calendar. So we got
How much are they?
they are free. So
Oh.
especially if you join me this Friday at Lindenwood Nature Preserve, I will have a bunch of these if you would like any of them. So yeah, these are all images taken by me with my telescopes, mostly my dwarf telescope, but some from others. So
Okay.
that was a pretty cool thing. But also I semi-recently got a dwarf and been getting really cool pictures from it. And my coworker's wife does art projects, and I gave her my first image of Andromeda and was like, hey, do what you will artistically with it. And my coworker just brought me the final thing today at work, actually, and I thought it would be cool to bring
Very
it in.
cool.
So
Yeah,
this
very
is what
nice.
she came up with. You can't see it right now, but she did use glow in the dark paint also. So when the lights are off, you can see all the stars and everything. Super cool. So I thought it would be a cool thing to bring in and share.
Yeah.
Excellent. Thank you. Yeah. Thanks for sharing that.
Yeah.
Are you selling those as well?
I'm not the one who did the painting ones. I can give you her contact information if you want it.
But you provided the initial image, so
Yeah,
you're good to go.
To light up some incense while you got that on the wall.
There you go. I see. Did you have?
Cool.
Yeah.
Right. Very good.
I just want to know who to pass the microphone on to.
Yeah, don't break it.
All right.
Thank you, Dale.
So I brought two things. They rolled up, so I might need some help. But first thing is it's a print solar image was taken the last week, and I tend to make these things for an office, and then provide them. People can do with them as they will. It's a 11 by 17. I also have an 18 by 24 that I have framed. So you can see some of the sunspots on there, this one actually had a little bit of gain turned up, so you can see some of the separation and intensity. I thought it was a cool look, and you get some of the glow in the background too. So
You have a logo.
yes, I do have a thing I put together. It's okay. The other thing is I brought some posters of GOES, and these are more just like show and tell from work, really. These are from NASA and NOAA, and these are
The satellite came out of Fort Wayne, so
satellite
you
optical
can be proud
payload.
of this.
Yeah, geostationary imager, so in geostationary relative to Earth because of its radius, and so that just allows you to have 24/7, 365 view of the same spot, and you park a couple around there, and then you just have this all the time view of the Earth. And all the other thing we do here is I'm now the project engineer on the cross-track infrared sounder, which is part of the Joint Polar Satellite System. So that one, instead of being geostationary, it's much closer, but it goes North Pole, South Pole, and the Earth rotates under, so you're able to get a full scan. And that's really looking at a lot of depth of a lot of infrared, like depth of through the air column itself, thousands of channels, so you get a lot of detail. So as opposed to the imager, which images, that one is trying to pierce into the actual column itself, and pretty cool. I mean, very accurate, so accurate that they have to input like noise into the data because otherwise you get divided by zero errors and stuff. Yeah, but it's I don't know as much about the sounder. I just started, so I got to get up to speed on it.
I see you brought 3 of the GOES 18 posters.
Oh, is that
What
2?
was your intent there?
No, I
Just 2?
put an extra one in there for some reason. I have no idea.
Oh, okay. So you're not giving them away tonight.
Oh, well, I mean,
It's up
if
to
you want one, I can donate.
No,
one.
I've got GOES 16 at home. So.
Okay. All right.
Not to brag, but I have more work in the 18 and than in the 16. So anyway, very good. All right. Anyone else? Anyone else? No? Yes? No? Okay, so anybody wants to see the recruiting materials that I've worked up so far, and you can judge them as harshly as you'd like. They're in the back corner, and I'll be there momentarily. Otherwise, that kind of close. Joseph, anything? No? Nope, can't talk yet. Can't talk yet. You have to repeat it. No one can hear you. Okay, go ahead.
Yeah, I didn't know if you wanted to ask for any information about observing groups that projects, but
Go ahead.
right. Kind of considering doing something along the lines of like one of the Messier marathons. Those are real popular this time of the year. But instead of looking for Messier objects, seeing how many of the satellites we could actually see or capture by radio over the course of some evening or doing it even during the daytime. It's kind of that same aspect of seeing how many you can capture in a certain period of time. I've been doing an awful lot of work with the radio that it was Kathy. Is that
Yes, Kathy Brown.
Kathy donated to the club, and just trying to see the variety of satellites that I can listen into, and how many. I got into this and didn't realize just how many newer satellites that they're putting on orbit just every day that are transmitting signals that can easily be picked up with that handheld radio. So I didn't know if that's something that the group would be interested, or doing it out at the observatory with some of my radio equipment to be able to listen to them as they're going overhead during daylight hours, or trying to schedule maybe a shorter period overnight to see how many satellites we could see visually or pick up by radio and know that they were going overhead. Just something I'm toying with. If anybody's interested in participating in something like that, my contact information is given in the newsletter each month under the Artificial Satellite Observing Program.
And Joseph, you're not only reaching the 25 or 6 people here, along with about the 6 or 7 that are on, we get a fair number of YouTube hits, views, that is, and so you're reaching a wider audience than just the 30 or so people that 30, 35 people that are in this meeting right now. So let them know. Certainly. Please do.
Oops. Yeah, I just want to say, I sent notice out to the board, and I neglected to send it out to the general membership, but we've got an all-sky camera build group that started up. So if you're interested in joining, don't need really a lot of experience, but basically the project is we've got a little camera that's covered by a dome, and it observes the entire sky, and we probably mount it simply on the post that's out there with all the utilities already. So it's already got a location. And so what do we get out of it? Well, first you got like a kind of a webcam that's out there all the time that we can probably hook into our web system, and people kind of, woo, wow, man, we got, like, you can take pictures of, you can see the stars, pure wedding. There's people on the web that have captured like meteor showers and, transient events like that. And it's also kind of cool to, you can actually tell if it's raining or if the sky's clear. Well, duh, it's at the observatory. So that's kind of pretty cool. We're estimated to cost probably around, I don't know, $500, and we might put out a funding request or something like that. But the software is pretty well developed there's like thousands of them, And I also saw today, it was pretty interesting, is NASA has like an all-sky camera network, and it was actually somewhat limited. When I saw, they only had about 10 of them, and they've got like 3 of them in Ohio and nothing in Indiana. But if they get 2 or 3 of them within about 50 miles, like if a meteorite passes over, then they say, no, I saw one there and was over there, but in this one I saw it and was over there, so they can triangulate and figure out all that cool stuff. And I was thinking, well, duh, why don't we, if we got like one here and another couple of, well, could we be part of the NASA network? I don't know,
Have to look into that.
I don't know. But any information or input you guys have, and geez, that'd be great. So I think the next meeting's in, I don't know, 2 or 3 weeks, and I'll stick it on the club calendar. So, all right, yay. Thank you.
You're good. Yeah, let's develop that NASA angle. NASA is our friend in a lot of ways, right? Well, okay. Anything to say about next month's meeting there, Sarah? Or is like, I don't know, start time, parking, show particulars, anything like that?
Yeah, so next month's meeting is not going to be in here. It's going to be at Science Central, same time. You can park in our front lot. We're located at 1950 North Clinton Street. If you need directions, let me know. Our front lot is going to be empty besides your cars, and the doors will be unlocked. And I'm going to have the whole museum on if you want to take some time to explore. But we're going to have a small planetarium program. I'm going to show off some of the cool things we can do in there. I'll give you a small tour of the stars digitally this time, and we'll conduct business as usual. But that's it. It's just going to be held at Science Central. Let me know if you have any questions, though. Okay. Can I pass this?
Is there a
That's
limit
right.
to the number of people you can handle in the planetarium?
Just to reiterate the question in case anyone didn't hear, was capacity. No, we're estimating about 50 people as our max capacity, but because I'm the planetarium manager, I can put in more chairs if needed. So, I know. I love my power,
I have a
but
bad back.
no,
Did I
I
ever
mean,
tell you that? I have a bad back.
tell anyone you might be that might be interested in coming out, even if they don't regularly attend these meetings. The more, the better, I think. Did you have a question?
Yes, would you recommend bringing like binoculars or something like that?
So I know a lot of you have visited Ball State and the Charles Brown Planetarium. In case you didn't know, I used to work there for 4 years, and boy, was I spoiled by working there for 4 years. Their star ball is incredible. Ours is from the late 60s and is from St. Francis. It's the Spitz A4 Planetarium star ball.
Yeah.
Not quite as cool as the Godot from Ball State, meaning you can, but I doubt you're going to be amazed by what you're seeing. The digital system that we have, the digital projectors, is pretty cool. It might be comparable to Ball State's, but the star ball is not going to be as spectacular. So you can, but save that for Ball State if you can. Okay. I was spoiled.
Can you show us the sphere?
Can I show you the sphere in space? You talking about the alien sphere?
The big ball.
The big science on a sphere? I thought you meant the alien space probe that people have said are out there. We have science on a sphere. We can absolutely show you science on a sphere. That's totally fine. That's what I've been working with for the last 6 years that I've worked at Science Central. So I'm an even more expert in that. Martin, if you ever want to give a presentation about worldwide weather and science on a sphere, you absolutely can. Martin and I work together to create a presentation in science on a sphere. If you don't know, it's just a 6-foot ball that hangs from our ceiling and we project things onto it. And it's just a very dynamic model. We can make Earth, we can make Mars, we can make, we can see Jupiter, we can see turtles moving across the oceans. We can see a lot of cool data. And that's what we worked on together, so.
The solar system science presentation is really good. That's the one we had at Pro Engineering Day.
Yeah.
That'd be a great one. That was good.
So because it's a sphere, it really shows off the planets pretty well. And we take a tour of the solar system. So we can do a small tour of the solar system and then go to the planetarium and take a tour of the stars. If that sounds cool with you.
Amazing.
Okay.
Okay.
And then the only other thing to note, I have 2 things real quick. One, I think I'm still searching for a speaker for October. I think we have November. We're kind of on a standstill right now, but we're working on it.
September?
And then
We have September then? September is good?
that's me. Yeah, that's me.
Oh, because last, in the eyepiece, it was shown to be open.
I have on my list
Well.
October
again,
and November free.
you're talking about
Let's.
in the eyepiece versus your list, so we just need to get it into the next eyepiece.
Okay.
Very good.
Sounds good.
Good. So we just have October. I thought I had a line on a speaker, and I'm still waiting for a response. It would be on amateur radio astronomy.
Okay.
I have a contact that has a near professional installation. I'm working on him, but I
Cool.
have low confidence. We'll see.
I'm fairly confident that I'm doing September
Okay.
with my presentation on my cohort to Chile and
Yes, I know we discussed.
observational astronomy. I
Great.
can send you the list in case we have any conflicting things.
Nope.
And we can get it all straightened out.
Good.
And then the very last thing, next week on Wednesday is the planetarium's grand opening. If you want to show up. It's at 10:30. It's going to be crazy busy. And that's it.
Thank you, Sarah.
Thank you.
That was good. Appreciate it. Anyone else? If not, we'll close. Thank you very much for coming, and stay warm and keep thinking about the sun and warm weather. Maybe next month.
70 by Saturday.
Hopefully.
Okay.
Thank you, everybody. Good night.